Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. In this video we're going to be looking at strong acids and how to calculate their pH, or the concentration of the strong acid from a given pH. Now, if you find this video useful, ensure that you like the video, subscribe to the channel if you haven't already, and then ensure that you also leave a comment if there is any other videos that you would like me to cover. So from the Bronsted-Lowry definition, an acid is something that releases a hydrogen ion, or a H+. We also call it a H+ donor. But within these Bronsted-Lowry acids, there are two different types, and they're on an extreme end of a strong acid and a weak acid. So firstly, let's just start with strong acids, which we'll be focusing in on for the rest of this video. Strong acids are those defined as being fully dissociated in a solution. Examples of any strong acids are mineral acids. So these include hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid. And when we say that any of these acids, these strong acids, fully dissociate in solution, what we're saying is that if you take a molecule of one of these and put it in solution, then it will break apart into its constituent ions. So if we take a generic strong acid, which we're going to just call HA, where A is the rest of the acid molecule. So for example, on these acid molecules here, we've just circled those rest of the molecule. And what happens is when it's in solution, it fully breaks down into the constituent ions. And so if we just take some examples here, if we look at a simple acid here, we're going to call these monoprotic or monobasic acids, HCl and HNO3. You can see that these are broken down into the two constituent ions, and you always need to just check that the charge on each of these combines to form neutral molecule in the backward direction. The reason it's called monoprotic or monobasic, doesn't matter, either way means the same thing in terms of how we use them, is because each molecule produces one proton or H+ ion. Hence the term monoprotic. And this gives us a really important relationship. Whatever the concentration of HCl is, because it fully dissociates when in solution, it's going to give the same concentration of hydrogen plus ions in solution. And you'll see later in this video why this is a really important relationship, that the concentration of the original acid you put in solution equals the concentration of hydrogen plus ions liberated on dissociation. You can also get polyprotic or polybasic acids. An example that we're going to look at is sulfuric acid and phosphoric acid. Now, sulfuric acid, because it has two hydrogens, it can actually form two hydrogen plus ions on dissociation. This is called a diprotic or dibasic acid because it produces two hydrogen plus ions. The ratio here is for every one sulfuric acid molecule, you get two hydrogen plus ions. This gives us the relationship that to work out the concentration of hydrogen plus ions, we need two lots of the sulfuric acid concentration. Phosphoric acid is a triprotic or tribasic acid, and it's clear to see that the number of hydrogens in these mineral acids is linked to the number of hydrogen plus ions that they liberate. And so the relationship between the molecule and the concentration of the phosphoric acid to the concentration of H+ ions is a 1:3 ratio. And so what we need to do is just multiply the concentration of the phosphoric acid by 3 in order to work out the concentration of H+ ions. Now, we talked about these H+ ion concentrations, and that's going to be really key with the next bit of information we look at, which is pH. Before we go any further, it's just worth noting what a weak acid is and how to differentiate this between a strong acid. So weak acids only partially dissociate in solution. And what that means is if you took, for example, 100 molecules of your weak acid and put it in solution, maybe only one or two of those molecules would actually break down into H+ and an A-. whereas the other 99 to 98 molecules would remain unchanged. So we show this quite simply by using a reversible arrow. You'll see that strong acids always have this irreversible arrow because all of the molecules go from this state to this state, whereas here they're fluctuating between. Now, obviously, if you're not given an equation to show what type of acid it is, i.e. you can't identify from the arrow alone, another thing to note is that any organic acid, like a carboxylic acid or phenol, is always a weak acid. The other weak acid that looks a bit like the mineral strong acids is hydrogen carbonate. So just be careful on how to identify those. So the reason we've been so concerned about the relationship between the concentration of acid and the hydrogen plus concentration is because these all link to pH. We know from previously that the concentration of the acid, HA, is linked to the H plus depending on the molar ratios and whether or not it's a strong or a weak acid. So for example, if we had HCl, which is a strong acid, then that would dissociate because it's monoprotic, linking to the molar ratios. For every 1 mole of HA, you'd get 1 mole of H+. So we need to take into these considerations when working out the concentration of H+. Once we have access to the concentration of the H+, then we can start to work out what the exact pH of that particular solution is. If you have the concentration of the H+, then to work out pH, you use the following equation. That is that pH is the minus log to the base 10 of the concentration of the H plus ions in solution. So before we go any further, some key things shown in this equation. First of all, the minus means there's an inversion of if we have a high concentration of H plus, we have a low pH. So this relationship here translates on the pH scale that you've done from very early on in your scientific careers, in the fact that the concentration of H+, if that is equal to 1 moles per decimeter cubed, then it's 0. Any greater than this, you actually get a negative pH, and that can happen. Really strong acids. Many of you would think that the pH scale only goes from 1 to 14 because that's what you're taught lower down in the school. Obviously 7 is 1 times 10 to the minus 7 moles per decimeter cubed of H plus ions, and then 14, unsurprisingly, is 1 times 10 to the minus 14. Just like before, any lower than this, and then you can actually get values higher than 14. And something to notice is that pH is always given to 2 decimal places, hence why on this pH scale here, they've gone to 2 decimal places there. And so whenever you're giving an answer, just make sure you round it to this level of accuracy. The reason pH is so important as a measurement in chemistry is because it gives an indication of the chemical conditions of a reaction or of a more complicated system. And these chemical conditions allow us to manipulate biological organisms, allows us to understand ocean chemistry and also agriculture in terms of soil, etc. If we had too many hydrogen plus ions, then the pH is obviously low, and that can affect enzymatic action. It can cause physiological damage. So it's really key, certainly for biochemistry, etc., to have an understanding of pH. In fact, the reason the pH scale was produced was by Mr. Sorensen, who was studying how to brew beer. And yeast are obviously biological organisms, and he needed to understand the correct chemical conditions for yeast to thrive, to brew that beer, and he came up with the pH scale as a result. And the final bit of key information is if we are given the pH, we can use this to work out the concentration of H plus ions, which in turn then allows us to work out the concentration of the acid that was originally put in solution. And so we need the opposite of this relationship going forward. And the opposite of minus log to the base 10 is to the power 10. So in order to get H plus, you basically just take whatever the value of pH is and do 10 to the minus of that value. So let's put all of this into practice by looking at two simple equations, and we're only in this video focusing on strong acids. So we're going to look at this question here. It asks, what is the pH of 0.4 mole per decimeter cubed hydrochloric acid? And we're going to use our 6-step approach for this. So our first step is to box the actual thing we're trying to calculate, which in this case is pH. And then we're going to underline any given values. And so we're given the 0.4 moles per decimeter cubed, but this is the concentration of HCl, which is actually our acid HA. Okay. Now, the second step gets us to write equations, both chemical and any useful mathematical equations. Now, this relationship we've discussed up here is going to be really key for this, because it directs you on what chemical equation you need to write. So we've been given HCl here and the concentration for it. But in order to work out pH, which is along here, we're going to have to make this stepwise approach. So we're going to have to work out the concentration of H+. So our chemical equation is going to be the ionization of hydrochloric acid, because we can use this concentration for the HCl to work out the concentration of H+ through the molar ratio. We know it's a strong acid because hydrochloric acid's on our list of mineral acids that are strong. Hence, we've got this irreversible arrow. And then with this, we'll be able to work out H+ concentration. And the mathematical operation to get to pH is that pH is minus log to the 10 of the H+ concentration. So our next step is to check the units of any given values. We've given the concentration in moles per decimeter cubed, which is absolutely fine because remember, square brackets is in moles per decimeter cubed. The only issue you'd have here is if you were given something in grams per decimeter cubed, that you'd have to change this, or if there was dilution or something. So then when moving on to the fourth step here, rearrange equation. Well, our equation's absolutely fine. So we're into 5, substituting the given values. Now we can't, because we've got concentration of H+ that we need to work out, we need to use our chemical equation to work out that in this step. As the concentration of HCl is 0.4, we know from our chemical equation from step 2 that it's a 1-to-1 ratio. So the concentration of H+ must also be 0.4 because it completely dissociates all of the concentration changes. And so then this allows us to work out that value and substitute it into the equation that we need. So therefore, our last step is just to calculate the pH, exactly what we're trying to get to. So in the calculator, you get the answer 0.397, and then we know that pH always is given to 2 decimal places, so we just need to round this up to 0.40. Now let's look at another style of question you can get with strong acids. So looking at this question here, we're going to use the same 6-step approach. We're going to box what we're trying to work out, which is the concentration of H2SO4. Sometimes you'll need to annotate and then underline any given values. So we know that the pH is 1.80. Now we're going to write the equations, both chemical and mathematical, that are going to be of use. So when you think about what we've been given the pH, so we're starting in this point here, and we're being asked to work out the concentration of H2SO4, which is this point here. So the mathematical operative that we need is to work out the concentration of H+ ion, which is 10 to the power 10 to the minus pH. And once we've used the pH to get to this concentration of H+ ion, we then need to use the molar ratios to work out the concentration of the sulfuric acid. So the chemical equation we're going to need is the ionization of H2SO4. And we remember that that is the diprotic or dibasic acid. Step is to check units of any given values. Well, pH is unitless, so we're absolutely fine here. Rearrange equations. This would only apply if you only learnt one of these and knew that Obviously, to do the reverse of minus log, it's to the power of 10, but we're going to learn both of them, so we don't need to do that. And substitute in the given values. So first of all, we've been given 1.80, so let's work out the concentration of H+. So we're just going to substitute that in, and then work out that the concentration of H+ is 0.016 moles per decimeter cubed. Again, this is only the concentration of H+. We've been asked to work out the concentration of the sulfuric acid that was used. And so, in order to calculate this, we need to look at the ratios that's in our chemical equation. We know it's a 2 to 1. We've just worked out that the concentration of H+ is 0.016. To go from 2 to 1, then obviously you divide that by 2. So we do the same operation to our concentration of H+ ions. And so when we divide 0.016, we get 0.008 moles per decimeter cube. And so that is our answer. And you can see how this really easy, simple calculation and set of relationships can be really useful in the lab. If you need to make a reaction go at a certain pH because it's optimum there, and that reaction could be something biological like enzyme activity is best at a certain pH, then really you can work out that concentration of sulfuric acid or whatever acid you're using that you need to make up. And this is why it's really key and is a key topic at A level. So we're going to start to look at some exam questions now. So this is an example, whilst it's only one marker, of a strong acid calculation. So pause the video here and have a go. Okay, so you should, if you've had a go at this, have come up with the pH as being 0.35 to 2 decimal places. And this is because we're trying to calculate the pH. The mathematical equation we need is minus log to the H+. To work out the concentration of H+, we need the concentration of the original acid. And the chemical equation for this, because it's a monoprotic, means that with 0.450 moles per decimeter cubed of nitric acid, we get 0.450 mole per decimeter cubed of the H+ concentration, because it's a 1-to-1 ratio. With that, you then input that into our pH calculation, and then we get our value of 0.3467, etc. And we're just going to round that up to get 0.35. Finally, to finish on, we have 4 questions here. I want you to use that 6-step approach plus the relationship that we've talked about at the beginning of this video in order to work them out. The 4th question is a bit of a curveball in that there is something a bit extra that you have to take aware of. But pause the video here and have a go and see if you can answer these strong acid pH calculation questions. Okay, I'm going to put the answers for each of these first and then talk through them. Okay, very quickly, I'm just going to put the workings out for questions 1 to 3, as these are the more straightforward ones. Just remember, we just need to round this up to 2 decimal place. Now, the 4th question requires something slightly different that we've not looked at in this particular video yet, but we have looked at in other videos. Trying to work out the pH, the given value actually is not in the correct units. We know that pH is the minus log of the H+. The square brackets here means moles per decimeter cubed, but this is in grams per decimeter cubed. So then when we get to part 3 of our approach to calculations, we know we're going to have to convert this into moles per decimeter cubed. In order to get from 10 grams per decimeter cubed into moles per decimeter cubed, we need to remember that in terms of units, volume is exactly the same. It's just the fact that this is expressed in moles, so N, and this is expressed in grams, which is a mass. And the thing that links N and M together is the equation N equals mass over mR. So if you're given a mass, then to work out number of moles, you would then divide it by mR to get into number of moles. Vice versa, if you're going the other way, you times it by the mR. In this example, grams per decimeter cubed is 10. The MR is the MR of H and Cl, which is going to be 36.5. So what we do is 10 divided by 36.5. That gives us our moles per decimeter cubed. And then what remains is use the equation. It's a 1-to-1 molar ratio. So we also get the same amount of H plus ions in solution. And then we input this value into our equation here and get the value 0.56. So this concludes this video on strong acid calculations. If you found it useful, as I've said at the beginning, ensure that you like the video, ensure that you subscribe to the channel, and then also leave any comments as to which videos you'd like to see produced next. In terms of in this series of videos, the next thing we will look at is strong acid calculations, but where dilutions are involved, and so this links to some of the work in year 1 videos. And then we'll be looking at weak acids and strong alkalis and how to calculate those.